Hello everyone, and welcome to the lecture for the NIMS Job Duty 2.5 project, otherwise known as the NIMS Step Block. This is a milling machine project, and it's a good one. There's not necessarily anything that new about what we're doing on this part. I mean, we've machined planar surfaces using the milling machine before, and of course we've drilled and tapped holes and things like that. We've chamfered holes, no big deal. But this part does give us opportunity to discuss some new things. We'll be using a handful of new tools. Specifically, we'll be using a roughing end mill to rough in the steps in the slot. We'll be using a carbide end mill to finish the steps in the slot. And we'll be using an offset boring head to finish this hole. But really, the challenge of this part is that there are quite a few features on it, and all of the features have critical relationships to one another. One really nice thing about this part is that if you get a 100% conformance part, meaning that it meets all of the print specifications with nothing being out of tolerance, then you can submit this to get your NIMS Manual Milling Level 1 certification. So NIMS is the National Institute for Metalworking Skills. The National Institute for Metalworking Skills. This is a nonprofit certificate granting organization. A lot of trades, maybe even most trades, have a state certification or accreditation which you have to get in order to practice that trade professionally. But machining is not one of those. That means that there is a very high degree of variability between how one machinist was trained and how another machinist was trained. What one machinist is able to do and what another machinist is able to do. What one machinist is expected to do at their job and what another machinist is expected to do at their job. The job classification of machinist is not very well defined. It's not standardized, there's no certification, there's no accreditation. This is compounded by the fact that there aren't really as many machinist apprenticeships as there used to be, right? So nowadays, most people get their training by going to school and then just learning on the job, as opposed to going through a proper apprenticeship. In order to fill that void, the National Institute for Metalworking Skills was formed. They've got a bunch of different certificates which students can achieve on different machines, different types of operations, different difficulty levels. In order to get the certificate, you have to do some independent study, take a written test, and then make a part. Everything on that part has to be in tolerance. That's what we call 100% conformance to the print specifications. In our classes, if you miss a tolerance, you miss a point. But you can still get a good grade in the class even if you miss a couple of tolerances. Not so for the NIMS certificate. Now, NIMS is really big on the East Coast of the United States. Somewhat less so on the West Coast, although it is starting to kind of gain a foothold here. You know, the nice thing about getting a NIMS certificate is that Laney College means something in our region, in the San Francisco Bay Area. But it doesn't really mean anything in Colorado, let's say, right? The NIMS certificates travel with you, and they mean something anywhere in the US. So it's worth trying to get the NIMS certificate if you can. Now, as I said before, this is the part for the NIMS Manual Milling Level 1 certificate, which I think is kind of surprising because this is a pretty ambitious part for what is ostensibly your first milling machine part ever. In our department, this is an intermediate project, and there are a lot of things that we can learn with it. It's an excellent, let's say, skill-building exercise. So let's go through the learning objectives here. Of course, you're going to demonstrate the safe operation and correct setup of the milling machine for both roughing and finishing procedures. You're going to develop your own planned order of operations. Okay, so that means that you are going to be making your own project planning worksheet. We give you some guidance, we give you the videos, but you're actually going to get just a blank project planning worksheet that you're going to have to fill out yourself. Now, like I said, we give you a lot of help with this, right? There are a lot of resources at your disposal, right? I mean, we do a little hand-holding, but still, you're going to be required to transfer it all to this formal document here. This is us slowly taking off the training wheels for your job planning abilities. In the third semester of the Manual Machining course series, Machining 230, we give you a little bit of background information if you're using a new tool, a new process, or if you're using a new material, but that's pretty much it, right? You get a project planning worksheet, you think it through, you fill it out, you bring it to your instructor, they look it over, you have a conversation, you might change it, and then you go out and you machine it according to your own plan that came out of your own brain. Not all journey-level machinists write out project plans like this, although more of them should. But for sure, this is the kind of detailed planning that goes on in a journey-level machinist's brain when they're preparing for a job. And that skill is just as important as, if not more important than, the ability to drill and tap a hole or cut a diameter on a lathe. So that's why we spend so much time on this type of stuff. All right, of course you're going to manufacture the part to specified sizes and geometric dimensioning tolerances. So that's part of the fun of this part. I mean, some of the sizes are kind of tight, but predominantly the interesting thing here are the relationships between all the features. And the last thing, you will determine the required tolerances. Okay, so there's actually some tolerances that you need to calculate on here, and inspect the part to determine whether or not it meets the tolerances for geometric dimensioning, for size, and for surface finish. This is a pretty interesting part to make, but for my money, the most interesting thing about this project is the inspection of this part. We'll get into that later. That will be its own video. So why is this project important? As I stated before, this project is really a skill developing or skill building exercise on the manual milling machine. You'll use many of the skills and techniques which you already developed in previous classes on previous projects, like the NIMS bench block, which we actually did on the drill press, and the angle plate, which was our first manual milling machine project that we did in Machining 210. So these are things like tramming in a head, squaring up a block, locating and making holes of different types, tapped holes, reamed holes, etc., and finishing surfaces to achieve certain tolerances for flatness, parallelism, and perpendicularity. But we're also going to be learning several new skills, like roughing end mills and using solid carbide end mills and producing slots and steps. That's something we actually haven't done before. As well as producing precision holes using an offset boring head, and we'll be using a few other specialty tools, specialty cutting tools, and specialty measuring tools on this project. A sizable chunk of the inspection of this part will focus on geometric dimensioning and tolerancing, tolerance of position controls, using the proper datum reference frameworks. It's actually much more complicated than you might think, and I also think much more interesting. And of course, we're going to do some strength training for that big old machinist brain of yours by going through the project planning process. Okay, I already talked about NIMS and the certification, so let's see. I think we're ready to move on to the print. Okay, so here's the print, and of course this is not one that we generated in the department. This comes directly from NIMS. Okay, so the material is cold rolled steel or mild steel, so that's just a low carbon steel. And this is the stuff we're going to use. This is 1018 mild steel that has a 0.18% carbon content, quite low. And this is cold rolled or cold finished, meaning that it is finished to size at the mill in the cold state, as opposed to hot rolled, which is when it's finished at the mill in its kind of red-hot state. It's a lot easier to finish in its red-hot state, but the problems are that it leaves a considerable scale on the outside surface. These corners tend to be more rounded over, and dimensionally speaking, it's not as accurate from the mill. The downside to using this cold-rolled stuff, though, is that there are more internal stresses built into the material because it was worked when it was cold. It's not super dramatic, but it is something that we're going to have to account for when we're doing our finishing operations. Basically, we have to account for the material moving around slightly during roughing. So the tolerance block down here is actually pretty generous. So for single decimal place dimensions, we get plus or minus 32 thousandths, so 1/32 of an inch. For 2 decimal places, we get plus or minus 15. For 3 decimal places, we get plus or minus 5. Angles are plus or minus 1 degree, and fractional sizes, I don't think there are any, but fractional sizes are plus or minus 1/64 of an inch, which is actually about as tight as the 2 decimal place tolerance. So that's a little weird. Anyway, so for the geometric dimensioning and tolerancing controls, they are specifying adherence to ASME Y14.5M 1994. So that is the 1994 revision of the geometric dimensioning and tolerancing standard, which is maintained by the American Society for Mechanical Engineers. This is kind of an old standard, but let's see, when was this print made? So it was made by DK, Donkey Kong, August 1st, 2001. Okay, so that kind of makes sense. There have since been 2 revisions after this one. So there was a 2009 revision and then a 2018 revision, which is the most current one. At some point, they're going to have to revise this entire drawing because there are actually a number of things that are kind of weird on this thing. And then hopefully they will update the specification. Okay, and there is a revision history block up here in the top right-hand corner. It just says Revision A, updated drawing and title block on March 7th, 2005, approved by L.W. Luigi Wario. This is a little bit weird because the title block does not specify a revision, but I guess this is supposed to suffice. There are also some general notes over here. So the finish all over is 125 microinches max. So yeah, I mean, you could probably do that with a hacksaw, okay? 2, break all sharp edges, 15 thousandths max. Okay, so they don't want any sharp edges on here. They want you to deburr everything, but not too much. Not more than 15 thousandths. And then all of the holes should be countersunk, so basically deburred, 30 thousandths max. So countersinking a hole is a diametral measurement. So 30 thousandths on the diameter is the same as 15 thousandths on the radius. So actually, these 2 notes are kind of redundant. But whatever. So before we get into any of these dimensions or GD&T controls, let's just look at the basic shape of this part. To me, it basically looks like a cube. I mean, not really a cube, right? Because some of the sides are longer, so a rectangular prism. But basically a cube-like shape, which has 2 steps and a slot cut out of it on the top surface, right? And then it also gets 4 holes also in the top surface. So basically there are 5 sides that you don't really do anything to, and then a bunch of work that happens on the top surface. Essentially a pretty simple part. The front view here shows you the sort of side profile of the part. The front view of a print is supposed to show you the view that gives you the most information about the overall shape of the part, and this definitely fits that. You can see some hidden lines here, which are of course the holes. They're inside the part. You can't see them because there's material right here, but if you had X-ray vision, then you would be able to see them. This hole right here is the same as that hole right there, and so that's a 1/4-20 UNC 2B threaded hole, right? And so that's why you see these 2 sets of hidden lines. One is the minor diameter of the threads, and the other represents the major diameter of the threads. You can also see that the threads don't go all the way to the bottom of the hole, and that the hole does not go all the way through the part. You can also see these cones here at the bottom of all 3 of these blind holes, the holes that don't go all the way through the material. And of course, those represent the cones that are left in the material by the drill point. So important to mention that up here we have, that's the depth symbol, a depth of 500 thousandths of an inch, half of an inch. So there's this kind of question about which one of these depths the callout refers to. Is it to the bottom of the threads, which would be this first one? Or is it to the end of the full diameter of the drilled hole, which would be the second one? Or is it down to the drill point, like this one? Well, I can just tell you that it's never the third one. It's never that third one. But for this hole, because the depth is given here in the same line as the thread specification, that means that it's this first one. It refers to the end of the full threads in the hole. From the top of the material where the hole is called out, so in this case it would be on the top of the slot right here, down to where the full threads end in the hole. So basically the way to inspect that is that if you can screw in a bolt half of an inch down into the hole, then you kind of meet the specification there. That's not a perfect inspection, but I mean it gets close to the sort of concept of what you're looking for here. Okay, but let's take a look at these holes. These two little holes here, 2 times, right? They're 2 little pinholes. Diameter 125 thousandths, an eighth of an inch, plus or minus 1 thousandths. Ooh, that's kind of tight actually. And that's also down a half of an inch. Well, what does that refer to? This one's a lot easier, right? Because there are no threads, so it obviously doesn't refer to the threads. And I already said that it never refers to the bottom of the drill point. So here it refers to from the top surface of the part, right here, the top of the one of these little tabs, down to the end of the full diameter of the hole. So where the 125 thousandths plus or minus 1 thousandths hole ends and the cone, which came from the drill point, begins, that is the 500 thousandths depth. I'll show you how to inspect that later on. Okay, the last hole on here is this 750 thousandths, so 3/4 of an inch plus or minus 5 thousandths, not particularly tight. Okay, and that one actually goes all the way through the part, and you can see that. Not because it says, sometimes it says through on the specification. Often misspelled like that, like THRU, all capitals. That means that it goes all the way through the part. There is no depth. But here it doesn't say that, right? It just shows you that it goes all the way through. So you have to interpret the hidden lines correctly in order to know that this hole goes all the way through the part. And if you look closely, you'll also see some chamfers, which are shown on both the entrance and exit of the hole. And of course, those are dimensioned right here, 2 times 30 thousandths by 45. In my opinion, this is kind of an awkward way to specify what is essentially a countersink. They are specifying it here as they would a chamfer. That makes it a little bit tricky to interpret this because this chamfer dimension refers to a single-sided or radial dimension. So actually you have to take 30 thousandths of an inch off of both sides of the hole. So essentially this is like a 60 thousandths by 90 degree countersink. So functionally, this 30 thousandths by 45 degree chamfer is the same as this countersink of 810 thousandths, because 810 thousandths is 60 thousandths over 750, which is the diameter of the hole, times 90 degrees. 45 degrees times 2 is 90 degrees, so that's the included angle of the countersink. And that countersink callout would just be applied directly underneath the callout for the diameter of the hole. But for whatever reason, that is not how they decided to do it here. Anyway, I've definitely gotten ahead of myself here, getting excited about countersinks and chamfers and pinholes and stuff like that. Let's take a step back and talk about the overall dimensions of this part. So a simple prismatic part like this has 3 overall dimensions, right? We have 3 dimensions of space, and therefore we have 3 overall dimensions for a part in 3-dimensional space. So based on the front view, we have a width from left to right, we have a height from top to bottom, and then if you look at the right side view, then we'll also get a depth, right? Essentially from the front of the part to the back of the part. So when you're trying to find the width, the height and the depth of the part, you're going to look at the front view and the right side view, typically. Okay? Sometimes you can find the depth in the top view. And you're essentially just going to look for the largest dimensions in those directions. So here, from the far left side all the way to the far right side of the part, we get this dimension, 250 thousandths. So that is definitely the width of the part. We also get from the very bottom of the part to the very top of the part this dimension, 1 inch 375, and that is going to be our height. And on this print, we get the depth in the right side view from the front of the part all the way to the back of the part, and that's going to be 1 inch 875. That is the depth of the part. Those numbers are important because when we're selecting our stock material, we're going to select a piece of stock which is just a little bit bigger than those 3 dimensions, so that we have a little bit of material to remove off of all of the 6 sides, but not too much, right? We don't want to waste too much time or material, but it has to be a little bit bigger, right? Okay, and then looking at the profile of the part here in the front view, we also have some dimensions for the steps. So we essentially have 2 steps, one here and one here, okay? And so this first one is going to be 750 from the bottom, and it's going to be 1 inch 500 thousandths from the far left side. The second step right here is going to be 1 inch 125 from the bottom of the part, and 1 inch from the far left side. Notice the way that these steps are called out, okay? They're called out from the left side and from the bottom. They're not called out from the top or from the far right side. So actually, the steps themselves are not called out, right? It's the material which makes up the steps which is called out. And they are called out from 2 surfaces which also happen to be datum reference surfaces, datum A and datum C. That little bit of insight can really help you to start planning out the order of operations and figuring out the priorities of different surfaces on this part. In the right side view over here, we can see the dimensions for the slot that goes through the center. It appears like it goes through the center of the part. So the slot has a width, which is the 875 thousandths dimension right here, and it also has a depth. But of course, again, in this case, they don't give us the actual depth of the slot from the top of the part to the bottom of the slot. They give us the material which is left over after the slot has been removed, and that's going to be 1 inch. So what do we get on the top view of the part? It looks like on the top view, this is where we get all of the dimensions which relate to the positions of the holes. So like for this big hole right here, that's 500 thousandths from the front of the part, which is datum feature D, by the way. So we have an A, a C, and a D here. And 2 inches, right, from the far left side of the part, which is datum C. This pinhole right here is 125 from datum C, 250 from datum D, so from the left and the front of the part. This top pinhole right here is 812 thousandths from datum C, left of the part, and 1 inch 687 from datum D, the front of the part. And the threaded hole is, 500 thousandths from datum C and 937 thousandths from datum D. Nothing terribly complicated there, right? I mean, all of these holes, they have a size, which we already went over, but they also have a location, right? In X and Y, right? You have an X coordinate and a Y coordinate, in this case given from datums C and D. But one thing you should notice is that all of those dimensions are in boxes. So that is fundamentally different than what we've got here for these steps. So this is a positional dimension, and these are size dimensions. These size dimensions here follow the typical rules where if there's no tolerance specified, then you default to the tolerances in the tolerance block. So here we've got 750 thousandths, that's 3 decimal places, and so that's plus or minus 5 thousandths. The From the left, this is telling me 1 inch 500, 2 decimal places, so that's actually plus or minus 15 thousandths. So the steps are tighter in the vertical direction than in the horizontal direction. Okay, not that interesting. But you can't do that with these dimensions in boxes, okay? These are called basic dimensions, and they are governed not by the tolerance block, but by the geometric dimensioning and tolerancing control which pertains to them. In this case, it's tolerance of position. That's what that symbol right there means, that sort of crosshair symbol. And the tolerance that it gives us is diameter of 8 thousandths with that little m. That's called a maximum material condition modifier. And then there are these 3 letters here, A, C, and D. What are those? Well, those are the datum features. Datum A, C, C, and D, right there. These are used as references to locate essentially the target position of these 2 holes. Actually, it's a lot more complicated than that. I mean, this this feature control frame here, which is what we call this sort of series of boxes with symbols in them, this is a whole can of worms, okay? And we're not really going to get into that now. We're going to do a whole video on inspection where inspecting and, well, actually interpreting geometric dimensioning and tolerance and controls for position, and then inspecting them is going to be a very major part of the video. Suffice it to say that this is a relatively tight tolerance, but it's not that tight. I mean, it can be achieved without too much anguish. You can kind of think of it as like, well, if this is a diameter of 8 thousandths, then that's a radius of 4 thousandths. So it's kind of like a plus or minus 4 thousandths, but not really, okay? And I'll explain what it actually means later, like I said, but for now, you can kind of think of it that way. Yeah, we also didn't talk about this perpendicularity control. This is controlling the perpendicularity of the center axis of these 2 pinholes relative to datum A, the bottom of the part. Yeah, that's a whole nother thing that we're going to go into later. But do notice that the 1/4-20 tapped hole and the 750 thousandths bore right there, they also have the same 8 thousandths positional tolerance. Okay, so that's actually shared between all of the holes on the top of the part. The slot also has a positional tolerance of 5 thousandths relative to datums A, which is the bottom of the part, and B, which is this datum right here. This datum is a little bit tricky because, well, it's attached to this extension line which is coming off of the front of the part, but hey, what the heck, so is datum D. So are these 2 datums redundant? Well, the answer is no. Datum D really is the front of the part. But notice that this datum identifier symbol, this flag right here, is coming off the extension line, but it's not aligned with any dimension line, these double arrowhead lines. Whereas datum B is. So this is kind of a rare and special case where if a datum identifier symbol is aligned with a dimension line, then the datum feature is not the surface that the extension line is coming off of, it's the center plane which is constructed between the 2 surfaces that are called out by that dimension line. So datum B is actually an imaginary center plane that goes right through the middle of the part between these 2 outside surfaces, the front and the back of the part. So essentially what this positional tolerance is saying is that the slot needs to be on center of the part. That's all it's really saying. But we'll go into this much more in depth later on. Okay, we're actually getting to the completion of what I want to talk about with this print. The last thing to talk about are the geometric dimensioning and tolerancing orientation controls. So let's start with this one right here. Those 2 parallel slanted lines, that's parallelism, within 2 thousandths to datum A. So what that's saying is that the tops of these 2 little tabs here, or these wings, need to be parallel to datum A, the bottom of the part, within 2 thousandths of an inch. Okay, let's look at this one. these two perpendicular lines, of course that's perpendicularity, perpendicularity within 2 thousandths to datum A. So that means that this surface, the front of the part, needs to be perpendicular to datum A, the bottom of the part, within 2 thousandths. Okay. And then over here we've got another parallelism callout within 2 thousandths to datum D. So remember that datum D is the front of the part, so this is datum D, and this surface right here is the back of the part, this one, and this surface has to be parallel to this surface within 2 thousandths of an inch. Okay, pretty straightforward. Okay, there's only two more, and these are going to be found on the top view here. So that's perpendicularity again within 3 thousandths to datums A and B. So this surface, which is the far left side of the part, so this surface right here, needs to be perpendicular within 3 thousandths of an inch to datums A, the bottom of the part, okay, that makes sense, and datum B, which we already mentioned is the center plane of the part constructed from the front and the back side. And over here we've got parallelism again, and that's 3 thousandths to datum C being this surface right here, right, it's called out right there, so this surface right here needs to be parallel within 3 thousandths to this surface. Pretty straightforward. But what maybe you've been able to sort of piece together here is that there's a kind of priority in these various different surfaces and datum features. So this is called out to datum A, this is called out to datum A, and then this is called out to this surface, which is called out to datum A. This is called out to datum A. This is called out to this surface, which is called out to datum A. So all roads lead to Rome, right? Datum A is by far and away the most important surface on this part because it's the reference for everything else. And if you look up here at the tolerance of position controls, you'll see that they're called out to datums ACD, ACD, ACD. So that means that datums C and D are also very important surfaces. Not quite as important as datum A, but very important nonetheless. So this is going to be really important when we go to do our inspection, because these are all going to factor into how exactly we fixture this part to be inspected. But it's also very important for our machining procedure. The sequence of operations in which we finish these surfaces is essentially going to follow the priority of the different surfaces. I mean, it doesn't have to, right? I mean, we can do it however we want to. That's the machinist's prerogative here, right? But it makes sense if datum A is the most important surface and everything else is referenced to that, we should finish that first and then align the part so that datum A is in the position where it's supposed to be before we cut, like, for example, this surface right here, which is supposed to be perpendicular within 3 thousandths to datum A, right? We should, we should do that after we have a good reference surface for datum A because it's finished. I hope that makes sense. Anyway, I think that that pretty much covers what I wanted to talk about with the print. Okay, let's talk about how to make the part. This is something that we give you in the project packet. This is called the NIMS Step Block General Procedure. Remember that we're not giving you a full project planning worksheet anymore. We're giving you this general procedure and of course the demonstration videos, but then you're supposed to take all that information and create your own project planning worksheet. You're supposed to populate this blank sheet with each operation, each tool you're going to use, and the feeds and speeds and depths of cut that you're going to use for those operations. Now, this general procedure gives you a lot of information, okay? But still, there are going to be many more steps on this sheet than there are here. For example, here it says drill and tap 1/4 threaded hole. That is one step, step 10. But of course there are many more necessary steps required to produce a threaded hole. So you have to find the position of the hole, you have to center mark that hole, you go in with the tap drill, then you go in with a countersink, and then you go in with a tap, And if it's a blind hole, then maybe you have to go in with a plug tap and then follow it with a bottoming tap in order to get full threads close enough to the bottom of the hole. So on the general procedure, all of that is just one step. But on here, you're going to have to break that out. Make sense? I hope so. Let's talk about the manufacturing process a little bit here, okay? The first thing, of course, is that we're going to get a piece of stock material. And it's going to come in a long piece of bar stock that is, maybe 6 feet long or something like that, with a certain width and height, and we're going to have to cut it off to a certain depth. Remember that we already know what the overall dimensions of the part are, so we have to select some stock material that is just a little bit bigger than those dimensions. So in this case, it's going to be 1.5 inches by 2 inches, okay? So the 1.5 is going to become the 1 inch 375 dimension, and the 2 inches is going to become the 1 inch 875 dimension. So we're leaving 1/8 of an inch for both of those dimensions. And then we're going to cut it off to a length of 2 inches 625 thousandths on the bandsaw. So the 2 inches 625 thousandths is going to become the 2 inches 500 width here. Okay, so again, we're leaving 1/8 of an inch for that dimension as well. And again, here's the block. So yeah, that's 1.5 by 2 inches. And what did we cut this off to? 2 and, this one's a little bit long. This is 2 3/4 of an inch rather than 2 5/8 right there. But, technically that is okay. It just means more roughing work, right? It's kind of a waste of time and material. Okay, so now that we've got the stock material cut, it's time to tram in the milling machine head. Now, this may or may not already be tram on your milling machine, okay? But at the very least, you have to check it, okay? Never assume. And then we're going to square the stock, following the same squaring up a block procedure which we used before on the angle plate, okay? It's exactly the same procedure. The sizes are going to be different, of course, because the part has different dimensions. But you can still follow that sheet that has the procedure for squaring up a block, as long as you know that the dimensions are different. We're going to use the octamill for this, okay? We like the octamill. Now, as part of that procedure, we're not only going to be squaring up the stock, we're also going to be machining it down to its rough dimensions, which are going to be 30 thousandths of an inch over all of those overall dimensions. And of course, we know what the overall dimensions of the part are because we covered that when we looked at the print, right? So 2 inches 500 thousandths is the width. And so you add 30 thousandths to that, you get 2 inches 530. I put that in parentheses, right, because it's a reference dimension. The 1 inch 375 thousandths height, you add 30 thousandths to that, you get 1 inch 405 thousandths. The 1 inch 875 thousandths depth, you add 30 thousandths to that, you get 1 inch 905. And lo and behold, that's what we've given you here in the procedure, right? We already did the calculation for you. So that 1.5 inch stock size is going down to 1 inch 405 thousandths. The 2 inch stock size is going down to 1 inch 905 thousandths. And then the 2 inch 625 thousandths length from the bandsaw cut is going down to 2 inches 530. Okay, so now the part looks like this. Squared up, machined on all sides. By the way, on the far right side of the procedure, we give you these isometric pictorial representations of the part at various stages throughout the procedure. So this is just going to help you visualize the various different steps and what the part is supposed to look like. Okay, the next thing we're going to do is rough out the steps and the slot. And that's going to be fun, because we're introducing a brand new cutting tool to your repertoire, the roughing end mill. The roughing end mill has these sort of serrations on the cutting edges. It's like it's wavy or scalloped on the cutting edges, like a bread knife or something. This is why this style of cutter is sometimes affectionately referred to as a corncob cutter. This type of tool is designed to take big, heavy, hogging cuts out of material. These things are freaking amazing. You are going to have a lot of fun, a lot of fun machining with these. So believe it or not, we're going to rough out the 2 steps and the slot in only 4 cuts. So that's 1, 2, 3, and then we're going to bury it right down the center, 4, and rough out the slot. So at this point we can basically consider this part all roughed out, okay? However, as you can see, there is a hole right there. Now that hole is not in the right place, but in any case, there is a hole that we need to consider. And we're actually going to rough that out now instead of putting the hole in right at the end. Because that hole is so big and it's so close to this sidewall. Actually, I mean, if you look at this one that was made correctly, you can see just how close it is to that sidewall. That if we finished all of the outside surfaces and then drilled that hole out, it would deform these surfaces here. So we're going to pre-drill it. We're going to rough it out by drilling it so that most of the material is removed, and then we're going to go in afterwards just to clean it up to the final size and put it in the correct location. So after we find the hole with an edge finder, we're going to use a center drill to mark it, and then we're going to go straight in with an 11/16 drill. So the final size of the hole is 3/4 of an inch. This is 11/16 of an inch. 3/4 of an inch is 12/16. So this is 1/16 of an inch smaller. That gives us 62.5 thousandths on the diameter to finish later on. And that's about 1/32 of an inch, or 31 thousandths, about 31 thousandths on the radius on either side. That's going to be plenty. You can see that we're going straight from a center drill to this big drill. Now normally this is big enough that we would have to pilot drill it. However, this is a special split point drill. Now we've talked about split point drills before, but just to reiterate, okay? Here on this drill, you've got 2 primary facets, and then behind the primary facet, I mean the grind, there's like 1 more secondary facet there, and that secondary facet comes up all the way to the center of the drill right there and splits the point, meaning it takes out half of this chisel edge, which is where the 2 cutting edges of the drill meet, or rather don't meet, because of the material that is in the core of the drill called the web. The web and the resulting chisel edge that is normally here on a drill is responsible for a lot of the cutting forces required to drill a hole. It's also the primary reason that these drills tend to walk around or wander and don't really cut straight holes. There are 2 ways to deal with it, right? You can either pre-drill the hole with a smaller drill that is just a little bit bigger than the web of this drill, or you can use a split point drill where the grind removes the point, which is what we're using here. Now we have a nice new Derrick's drill sharpener, which can put a beautiful split point grind on one of these drills. I will have to show you how to use that when we get out into the shop, but you should be able to use it, and you know, you can grind or regrind your own drills this way. So there's really no excuse to use a dull or broken drill. I mean, we make it really easy with that drill sharpener. Okay, so at this point, the part really is roughed out, and we can move on to finishing operations. As I mentioned before, this part is essentially a rectangular prism, and 5 of the sides don't really get any work done to them, only the top. So we're going to finish those 5 surfaces first, okay, and then we're going to do the top last. And the sequence of operations we're going to use to finish the outside surfaces is the one that we already specified based off of the priority of surfaces that comes from the print. So we're going to use a fly cutter to do this, just like we did on the angle plate project, okay? And we're going to finish datum surface A, which is the bottom of the part. Then we're going to do datum surface C, which is the second in priority, so that's this surface. Then we're going to do datum feature D, which is this surface. And then we're going to do the 2 surfaces opposite C and opposite D. Okay, that's not exactly how I'm going to hold it in the vise, okay? It's just, I'm trying to hold a lot of things in my 2 hands here, okay? But that's the sequence. And that is also specified right here. So the next thing is to finish the steps and the slot, and we're going to use another fun new end mill. The solid carbide end mill. Yes, it is made entirely out of solid tungsten carbide. It's heavy, it's hard, and it's also extremely expensive. And to top it all off, it's also very, very fragile. So we're going to ask you to please take very, very good care of these tools. There's a little bit of a question about whether or not you should even be using these on a manual milling machine. They're really designed more for like CNC, where there's a very smooth, predictable, controllable movement with flood coolant all the time. But these are really, really common in industry, and so we want you to get exposure to them. That's why we're using them in this project. Okay, so we're going to finish the bottom step first, then we're going to finish the top step, and then we're going to finish the slot. Pretty straightforward. Finishing the slot is kind of tricky. Like, how do you get it perfectly on center? And how do you verify that it's perfectly on center, right? And then how do you measure the width? These are all good questions, which we will cover in the demonstration video. So at this point, all of the planar surfaces on the part are complete. Okay, so now all we need to do is finish the holes. We're going to start with this big 3/4 inch bore right here that we pre-drilled earlier, and this is going to be another opportunity for us to use a cool new tool. This is an offset boring head. It essentially allows you to single point bore a hole like you would be able to on a lathe. So you take one of these boring bars, okay, this one just happens to be an indexable carbide boring bar. It's got a 1/2 inch shank, and that fits right there in the offset boring head. So this R8 taper goes into the spindle, right? And so when you turn the spindle on, then you can see that the cutting edge on the boring bar begins to sort of inscribe a circle. So like I said, this is just like on the lathe, except that on a lathe, the workpiece is spinning and the tool is stationary, and here, the workpiece is stationary and the tool is spinning. But the effect is the same, right? Now, in order to change the size of a hole on the lathe, you move the cross feed in and out in order to change the position of the boring bar. With an offset boring head, there is a built-in lead screw in the head itself, and you move that dial with an Allen wrench, right, in order to move the head in and out this way, right? And that will shift the position of the cutting edge, and that's how you change the size of the hole. Very cool, very useful, capable of producing extremely precise holes of any size that you want, and important for our process here, it is also able to locate a hole wherever you want, regardless of where the original pre-drilled hole is. Anyway, we'll go over this during the demonstration. Let's also not forget about the chamfers on the two sides of the hole. Okay, this one actually we're going to save to the end because we have to flip the part over and finish the backside to do it. Okay, but this one we're going to put in right now, and we're just going to use a nice big fat countersink. And there you go. Okay, we're almost done here. We only have 3 little holes to finish, and we can start with the pinholes or start with the tapped hole. It really doesn't matter. On here it has us starting with the tapped hole. So once you locate the hole, then you drill and tap it. But one big thing that we're going to be doing differently here is instead of using those junky old keyless drill chucks that we've been using up until this point, we are going to be using this Albrecht precision drill chuck made in Germany. This is the super hot whammy of drill chucks. Ultra Präzision. We only use these for this project, and only because we have to, and because we trust you at this point. You have graduated. You have truly come of age. Now you can use the best tools. But mark my words, if you spin a drill in this drill chuck, I will never forgive you. Anyway, so we'll go in with an edge finder first, of course. And actually, one of the cool things about these edge finders is that they don't need to be held very precisely. What I mean is that the axis of the shank of the edge finder does not need to be spinning super concentrically to the spindle axis in order to find an edge very accurately. This is a little bit more complicated than I want to go into here, but essentially because this is spinning, the part that's wobbling down here is always going to find the edge relative to the true axis of rotation. Pretty useful stuff. Okay, number 3 or number 4 center drill. Number 8 tap drill. And this is a stubby screw machine length drill that's got a split point on it. Okay? It's also got a significant percentage of cobalt in the mix of the alloy, so this is very heat resistant and wear resistant. Why do we use a number 8 drill? Well, you can always reference the handy dandy tap drill and decimal equivalence chart that we give you. And if you look at the quarter 20 threads here, it says that a number 7 drill is the correct tap drill. So that's 201 thousandths in diameter. But we're going in with a number 8 drill, which has a diameter 2 thousandths smaller, 199 thousandths. We're doing this only because, in our experience, it is easier to hit the tolerance for pitch diameter if you use a number 8 rather than a number 7. So, I mean, it's easier to get the go gauge to go and the no-go gauge not to go if you use this slightly smaller drill. That's all. Okay, and then we're going to go in with the quarter 20 tap, and we may even have to go in with a second tap. So this first one has a plug-style chamfer on the end of it, so it's like 3 to 5 incomplete threads on the end of the tap. This helps it center on the hole and distributes the cutting forces more evenly, but the problem is that you won't be able to get full threads as close to the bottom of a blind hole. And so we're supposed to get, let's see, well, a half of an inch of full threads is what the print says. So that's a quarter 20 tap, 20 threads per inch. So that would be 10 threads per half of an inch. So we need to be able to get 10 full threads or 10 turns of this tap in the hole. We may or may not be able to do that before we run out of room at the bottom of the hole. So we'll start with this tap and then we'll follow it, if need be, with a bottoming tap, which only has like 1 to 2 incomplete threads at the end of the tap there. This whole first going in with the plug tap, then finishing with a bottoming tap when you're tapping a blind hole business should not be new to you. We have done this before. Oh, and how could I forget? We got to countersink the hole, okay? So we're actually going to do that before we tap it. This is going to open up the mouth of the hole and create an entry chamfer so that there's like a gradual start to the threads instead of a sudden start. That will keep the threads from getting smushed or rolled over later on, and it will also help the taps to cut and find their location. Okay, and now it's time to do these 2 little 1/8 diameter pinholes. Again, using the precision drill chuck, we're going to go in with a center drill, but a tiny one, an adorable little tiny number 1 center drill, okay, because it's a very, very, very small hole. Look at how cute this thing is. It's not even like a real tool. Anyway, and then we're going to go in with another drill. This is, again, a stub length drill, which is also made out of a high cobalt alloy. It's got a split point on it, right? So this is real rigid. It's got a split point on it, so it's not going to walk, it's not going to flex, okay? It's going to drill a nice straight hole wherever we tell it to, which is what we want. And why are we picking a number 32? We're going to finish this hole with a reamer because of the tight size tolerances required. Okay, it's 125 thousandths, 1/8 of an inch, plus or minus 1 thousandths. That's a little tight to finish with a drill. But of course, if you want to ream a hole, you first have to drill it. Now, the size of the drill that you select is determined by how much material you want to leave in the hole for the reamer to finish, which should be about 6 to 15 thousandths of an inch is all the reamers really like to take, although this is definitely dependent on like the size of the reamer. Bigger reamers can take bigger cuts, but as a sort of general rule, this definitely holds true. So if we look at the drill chart, right, we can see that a number 32 drill right there is 116 thousandths of an inch in diameter. The final size of the hole is 1/8 of an inch, or 125 thousandths of an inch, and so the total difference there is 9 thousandths of an inch, and that's all the material that the reamer is going to take. Like if we tried to go in with a number 31 drill, that's 120 thousandths, so that would only be 5 thousandths of an inch to cut, and you know, that's really cutting it a little close. No pun intended. So we'll use a number 32. Okay, and the very last thing that we need to do, and we can't forget to do it, is we need to countersink the backside of the 3/4 inch hole. So we'll hold it in the vise like this, and we'll refine that hole, and then we'll just use the countersink again to put a nice little countersink on there. And then that's it. The part is done, and it looks beautiful, and, you know, hopefully it passes inspection. Okay, so we are almost done with this lecture. All right, here's the inspection report. It's a doozy, all right? But we'll have to go over that in another video. The final thing to talk about is where are you going to find the data for feeds and speeds? For a lot of these tools and operations, you can use the tried and true feeds and speeds chart in the operations manual on page 8-2 in the vertical milling machine section. So for things like drills and reamers and fly cutters, this all applies. Also remember that the chart in the vertical milling machine section does not have any data for feed rates, okay? Because back in the day, it was assumed that you're going to be hand cranking these tables. But if you flip over to the horizontal milling machine section, then you're going to find the relevant information for how to calculate feed rate, right? So you'll have the calculation right here, and you'll also get a chip load per tooth in all of these little boxes here, okay? So you can use that to your advantage. But for the two special end mills that we're using on this project, the roughing end mill and the carbide end mill, don't spin, don't you do it, it would be better to use these charts which we provide for you in your project packet. So one for roughing end mills and one for carbide end mills. And these charts do give you both a surface feet per minute, which you can use for calculating the spindle speed, and also a chip load per tooth that sort of depends on the diameter of the tool, right? A bigger, beefier tool can handle more of a feed rate, right, without snapping. And then the last thing in your project packet are these two sheets right here. And these came from the website of the Criterion Manufacturing Company, which is the company that manufactures the offset boring heads that we use. So this first sheet just kind of tells you what the different parts of the tool are and how to adjust the position of the boring bar to adjust the size of the hole that you're boring. And then the second sheet gives you the cutting data. So we're over here in low carbon steel, okay? And then I would recommend that you start off with these values here, the uncoated inserts, and actually ours are coated, but you know, I have really found that it's not the insert, it's not the tool that is the limiting factor here. It's the fact that this is an inherently unbalanced tool. And so what happens is that you start running into vibration and chatter problems, and that's the thing that limits how fast you can spin it, okay? So it's not necessarily about what this can handle. So in my experience, a good starting position would be the lower range here, 350 surface feet per minute, the lower range of the uncoated inserts column. But as I'll show you in the demonstration, this is something that is kind of an experimental value, and you will need to practice a little bit and really dial in the speed and the feed rate and the depth of cut to get a really nice bore. All right, folks. I think that's it. I think that gives you everything that you need in order to translate the print and the general procedure into a detailed project planning worksheet for this part. When you're done with the project planning worksheet, or think that you're done with the project planning worksheet, turn it in to your instructor to be reviewed. Your instructor is going to look through this, mark it up, and then you're going to have a conversation about it. And then ultimately, your instructor might require you to make some changes and then resubmit it. Okay? This isn't punitive, right? I mean, the whole point of this is that you think about it a little bit, you bring it to your instructor, and then you have a conversation. I mean, to me, one of the most rewarding things about machine work are the kinds of conversations that you can have with your colleagues about the process. You can learn so much from the people that you work with, whether they are at the end of their career or at the beginning of their career. Everyone has some kind of insight. As an instructor, I learn a lot from my students. I'm sure that my students learn a lot from me, but it's that interchange that makes everybody better at their job. So, have fun with it. Anyway, so that's it for this lecture video, and the next video is going to be part 1 of the demonstration in which we perform all of the roughing operations. I'll see you then.